In this video, we're going to talk about buffers. We're going to apply the concept of conjugate acids and conjugate bases. This is a concept that only exists within the definition of the Bronsted-Lowry conception of acids and bases. You can't actually have conjugate acids and bases under the Svante-Arrhenius definition of acids and bases. So what is a conjugate acid or a conjugate base? They are the complementary acid or complementary base that is formed as a result of an acid acting like an acid, according to the Bronsted-Lowry definition. When an acid behaves like an acid, it becomes a base after the reaction is finished. And likewise, when a base behaves like a base, in the reaction, it reacts as a base, it does its base thing, and then it becomes an acid. It's what's left over after the reaction is finished of an acid or a base. So every acid becomes its conjugate base. An acid becomes a conjugate base. Now, the only difference between whether a compound is sort of natively an acid or a conjugate base really has to do with where it's derived from and how we normally see that particular compound. Do we normally see that compound existing free in nature, or do we see the compound only as the result of a reaction that's occurred between that acid and some other base, or between that base and some other acid? Otherwise, these are relative terms, in other words. Otherwise, there's no real reason to call one compound a conjugate of a different compound. So every acid becomes its conjugate base, and every base becomes its own conjugate acid. So for example, what is the definition of an acid? It's a proton donor. So take hydrochloric acid, HCl. So as an acid, hydrochloric acid will donate away its hydrogen to something else, usually to water. When you dissolve hydrogen chloride in water, you get hydrochloric acid solution. And in that solution, the hydrogen ion leaves the chloride and joins to a water molecule to make hydronium ions. What's left of the hydrochloric acid then? Well, not really much of anything at all. What's left after hydrochloric acid donates away its hydrogen is simply the chloride ion, which isn't much of an acid at all, is it? It's not really much of an acid. It's more like just a simple ion. Nevertheless, this is called the conjugate base. So in this context, we don't just simply refer to the chloride ion as a simple atomic ion, but we refer to this in the context of acids and bases. We would say that this is the conjugate base of HCl. It's what's left after the proton has been donated away. After the proton has left the acid, whatever remains behind is the conjugate base. Almost always that means it's a negative ion, because hydrogen ions, of course, are positively charged. Once you take a positive away from a neutral, once you have something neutral and you lose a +1 or +2 charge, what do you end up with? You end up with a negatively charged thing. 0 minus +1, 0 minus 2 +1s, you end up with negative charges. So almost always, in fact, I'm hard pressed to think of a time when your conjugate base is not a negative ion. Let's take another example, sulfuric acid. Sulfuric acid, H2SO4. Donates one of its protons. Remember, the first deprotonation is strong for a strong acid. Sulfuric acid, of course, is a strong acid. Its first deprotonation is strong. The second deprotonation is weak and much weaker, therefore, because it's hard to remove a positive charge from a negatively charged ion. So we're only focusing on the first deprotonation. But when hydrogen sulfate, when sulfuric acid loses or donates one of its protons away, what's left? The bisulfate ion, or the hydrogen sulfate ion. The hydrogen sulfate ion, whoops, wrong one, is the conjugate. It's the conjugate base. Now, all that word conjugate means is that this is a base molecule, this is a base ion or base compound that was derived from or came from sulfuric acid losing one of its protons. That's all this means. That's why we use the word conjugate. On its own, the hydrogen sulfate ion, outside the context of acids and bases, is simply a polyatomic ion. There's nothing special about it. There's no reason for special terminology. But when we're in the context, if we're talking about acids and bases, in that context, we could refer to bisulfate or hydrogen sulfate ion as a conjugate base of sulfuric acid. Or we could actually see bisulfate ion as an acid in its own right. How do we see that? Well, again, these are relative terms. Conjugate is a relative term. Relative to what? Well, it's a conjugate base relative to the acid it came from, or it's an acid relative to the conjugate base of itself, of hydrogen sulfate. So for example, you could take hydrogen sulfate ion and you could actually observe its second deprotonation. You could deprotonate it, and I don't have enough room to write the entire word, deprotonate, and you'd get what? Well, you'd get another donation, you get that second proton donated, and you'd end up with the sulfate ion. Now, the sulfate ion in this context is the conjugate base of what? It's the conjugate base of the acid, the hydrogen sulfate ion. But you just said that the hydrogen sulfate ion is a conjugate base. Yeah, but only relative to the sulfuric acid. Relative to sulfate ion, hydrogen sulfate ion is an acid. So it's all relative. It depends on what you're speaking about, what you're comparing it to. Sulfuric acid is an acid. If somehow, you're not really likely to do this, but if somehow you could shove another proton onto sulfuric acid, which I don't believe you ever can, it would be very unstable. You would have to be a super strong acid to do this. But if somehow you could actually manage to shove a proton right onto one of these oxygens on sulfuric acid and make H3SO4 plus, that's what it would be, by the way, H3SO4 plus. If you could do that, that would become the conjugate acid of the base sulfuric acid, a sulfuric acid base. Okay, so that would be, I guess that would be sulfuric base. Such a thing doesn't happen. The reason these are named the way they are, that sulfuric acid is named as the acid rather than the conjugate base of some hypothetical H3SO4 plus, is because you really never see this. This does not happen. Some molecules are just the way they are. You're not going to find them doing things unexpected. Likewise, you'll never see most of the things that we call acids acting as bases. And it's very rare, although it is possible to see. It is possible, but very rare to see bases act as acids, though it is possible. And we will actually look at one of our bases acting as an acid as an example further down. So that's the idea. And everything I'm saying about acids applies equally well to bases, only according to the definition of bases. So the definition of an acid is a proton donor. So when an acid donates its proton, whatever's left is a conjugate base. But if that conjugate base has another proton that it can donate, then that conjugate base itself can in turn become the acid of a further deprotonated conjugate base, a second or third deprotonation resulting compound. Let's look at a couple more examples. How about carbonic acid? Well, carbonic acid is another diprotic acid or polyprotic acid, meaning it has more than one proton to donate. The first deprotonation of carbonic acid results in the bicarbonate ion, which is the conjugate base of carbonic acid. So relative to carbonic acid, bicarbonate or hydrogen carbonate if you prefer. By the way, I say bi just because it's a lot easier than saying hydrogen. Hydrogen carbonate and bicarbonate are the same thing. Hydrogen sulfate and bisulfate are the same ion. Just remember that bi, the prefix bi, is just another way of saying hydrogen. when you're talking about ions. Only when you're talking about ions. Okay, so the bicarbonate ion is the conjugate base of carbonic acid. If you were to deprotonate bicarbonate ion, however, you could get, this is a very weak acid, but you could get one more deprotonation out of this and end up with purely carbonate ion. And the loss, this would be your second deprotonation, your second dissociation. So second deprotonation, deprotonation. So that would make bicarbonate ion your acid in this context, and the carbonate ion would be the conjugate base of bicarbonate ion. So it's all relative to what you're comparing the compound to, or what you're comparing the ion to. If you're comparing it to its parent, its ultimate acid parent, then it's a conjugate base. If you're comparing it to the next deprotonation result or product, then it's actually an acid. And then you call that thing the conjugate base. The conjugate base of water, we've already talked about the conjugate base of water, but just as a reminder, water, remember, you can think of water, remember, it's amphoteric, but you can almost think of it as what? As a diprotic acid. You lose one of the protons, you get hydrogen ion plus hydroxide ion. The hydroxide ion is, of course, your conjugate base of H2O. And in this context, H2O would be your acid. Remember, water is amphoteric. It can act as an acid in some circumstances. It can act as a base in other circumstances. It really just depends on whether it's around an acid or a base. If it's around an acid, water will act as the base and accept the acid's proton. If it's around a base, water will act as an acid. Wait, what did I say? Yeah, water will act as an acid and donate one of its own protons to the base to become a conjugate base. So the conjugate base of water is hydroxide ion. Its conjugate acid, if you recall, was hydronium ion, H3O+. And what is the conjugate base of acetic acid? Well, we know the formula for acetic acid is HC2H3O2, hydrogen acetate. So its conjugate base would be whatever results after the loss of its proton. And what would that give us? Well, that would give us, well, you'd get a free proton, right? That would be floating freely in solution, probably joining with water to make hydronium ion. And then the other part of this would be the negative ion, the acetate. Actually, it's right here. It's the acetate ion. Acetate ion is the conjugate base of acetic acid, or hydrogen acetate, if you prefer. You should call it acetic acid, though. Base examples work exactly the same way. So base examples, hydroxide, if the conjugate base of water, which is hydroxide ion, if you take that without referring to the water where it came from, if you simply take a hydroxide ion and you add a proton back to it, you get water. And so in this circumstance, water would be the conjugate acid of hydroxide ion. What would be water's conjugate acid? Well, we just said that, right? H2O, however, can act as a base and accept a proton very weakly, but it can, and it would form H3O+, which would be the conjugate acid of the base H2O. So it's all relative. It's all a matter of accepted Lowry Dutch. This concept, acceptors are acids, proton donors. Sorry, proton acceptors are bases, proton donors are acids. So what about ammonia? When ammonia, NH3, accepts a proton, when ammonia, the base, acts like a base and accepts a proton, takes a proton, what do you get? Well, you get the conjugate acid of ammonia, which is ammonium ion. What makes this an acid? The fact that you now have a fourth hydrogen on ammonia. That fourth hydrogen is now available to be donated away to some other base if another stronger base comes along. Ammonium now has the capacity to donate that proton. You might ask, well, didn't it have the capacity to donate any of those other 3 protons, those hydrogens, I should say? Yes, but not very likely. Remember, just from experience, this is not, you can't really logic your way to this conclusion, but through experience, we know that some compounds are more willing to part with their hydrogens than others. Technically, you could rip the hydrogen off of any molecule if you provide a strong enough base next to it. But in practice, most molecules under regular conditions are only going to act either as acids or bases. And it takes extreme conditions to make ammonia act like an acid, but we will see that it can. We'll also see situations where otherwise inert molecules can have their hydrogens ripped away from them by super strong bases. But that's not the norm. I just want to emphasize this. Compounds are referred to as acids or bases by the way they normally act under normal everyday circumstances, not in the presence of super highly reactive acids and bases, like super acids and super bases. You don't define things by extremes. You define things by their everyday average. Okay, how about this? I'm already doing these on the next page. All right. Well, anyway, so we have this one. This is called methylamine. You've seen this before if you've seen the previous video. Methylamine or aminomethane, either way, CH3NH2. So when it accepts a proton, you get methylammonium ion. Notice what happened here. We went from NH2 to NH3. For bases that accept protons, it's always the nitrogen that accepts the proton. Why do you suppose that is? Well, it's because the nitrogen has the lone pair. This lone pair on nitrogen, whenever nitrogen is bonded to carbons and hydrogens, there's always a free lone pair. That lone pair allows for the creation of a bond with a hydrogen ion. Remember, the hydrogen ion has absolutely no electrons. H plus, the plus sign there means hydrogen. This hydrogen has lost its one and only electron, so it has no electrons. Well, what do you need to create a covalent bond? You need 2 electrons, right? Well, ammonia and its derivatives, nitrogen compounds, tend to have 2 electrons, a lone pair, and it uses both of its own electrons to create the covalent bond. In other words, it donates both electrons to the covalent bond between itself and hydrogen. This is referred to as dative bonding, D-A-T-I-V-E, bonding. Dative bonding is just another kind of, it's a covalent bond. It's just a covalent bond where only one of the atoms is donating both of the electrons itself. It's facilitating the bond all by itself. Nitrogen facilitates the creation of a covalent bond between itself with hydrogen ion, because hydrogen ion has no electrons to donate. So nitrogen generously says, well, okay, I'll supply that extra electron that you, hydrogen ion, would have supplied if you had an electron. I'll just put up both electrons and we'll form a bond this way. Now, of course, anything that's positively charged that gets added to something that is initially neutral, a 0 plus a 1 charge gives you a +1 charge. So anytime you see something getting protonated, you should see that its charge, its positive charge, increases by 1 for every hydrogen ion that accepts, that every proton or hydrogen ion that it accepts. So how do you figure out the conjugate acid? Simple, just add another hydrogen to the nitrogen and add a +1 charge. And that's how you figure out the formula for the conjugate acid of a base, of a Bronsted-Lowry base. What about hydroxides? Well, metal hydroxides don't typically accept protons. Hydroxide ions do, but when they do, they simply become water. So you're not going to see too many situations where you see, a Svante Arrhenius defined base accept a proton other than the hydroxide ion itself? And of course, water can accept a third hydrogen, a third proton, to become hydronium ion. What is the conjugate acid of cyanide? What is the conjugate acid of cyanide? Well, cyanide ion, you know, I just said that nitrogen is the one that always accepts, but in this case, in cyanide ion, because carbon also has a lone pair, in this case, it's hydrocyanic acid. The carbon has a lone pair that it donates, and this time it's the carbon that forms the data bond in hydrocyanic acid. HCN, hydrocyanic acid. And you've seen this molecule before. And by the way, the answer is over here for both of these. So hydrocyanic acid. It's very rare that carbon ever has a lone pair, right? There are only two molecules or a molecule and an ion that you've seen, carbon monoxide and cyanide. I'm pretty sure you can't think of another instance where you've seen carbon with a lone pair on it in a molecule or an ion on the carbon itself. Okay, so let's do some more examples. Actually, these examples, you've already seen them. We're just going to do them again. We just saw methylamine, but just to sort of like spell it out, let's take a look at ammonia. NH3. So we have ammonia. When we put ammonia, let's say we put ammonia in with some kind of an acid, let's say hydrochloric acid. So we mix ammonia and hydrochloric acid. Ammonia is a gas, but you can dissolve it in water. And once it dissolves in water, it actually creates something else, but we're not going to worry right now about that. We'll just say ammonia, the molecule, somehow dissolves in water. What do we get? Well, we're going to get a transfer of protons onto the ammonia. And so we're going to make ammonium. So that 3 becomes 4. Why? Because of that hydrogen. In fact, maybe it's better if I draw the arrow like this. So we end up with 4, NH4, ammonium ion and chloride ion. Ammonium, and actually we end up with the compound ammonium chloride. Ammonium chloride. But ammonium chloride dissolves well in solution. So really what you get is ammonium ion floating freely, aqueous, and chloride ion floating freely in the water, in the solution. In solution. So ammonium ion. And so the conjugate acid of ammonia, the conjugate acid of ammonia is ammonium. By the way, the chloride is the conjugate base of HCl. But this is conjugate acid examples, right? So conjugate acid of ammonia. So we create ammonium from ammonia. Okay. Methylamine, again, CH3 NH2, and this nitrogen has a lone pair, which it can use to create a bond between a proton and itself. So let's say, again, we put this in, we add some sort of acid. It doesn't even matter what the acid is. In fact, I'm going to forget about even writing out the acid because this is the conjugate acid example. I don't even. Let's just say it's in the presence of hydrogen ions floating freely in solution. So what happens? Well, the hydrogen ion will attach itself to the nitrogen so that we get CH3 NH2. In fact, here, let me do a little color coding for you. Let's make it, so we end up with this, and this ends up having a, whoops, how'd that happen? This ends up with an overall positive charge. Why? Because we added a positively charged ion to an otherwise neutral molecule. So the result is a positive ion, which is called methyl ammonium ion. Methyl ammonium ion, methyl ammonium ion. You don't have to learn the name of that, but I'm just letting you know it becomes an ion because it now has a positive charge. And it now has an extra hydrogen. And you'd write that out. You don't have to write it like that. You could just write out the whole thing, CH3NH3 positive charge. By the way, this is not ammonia anymore, right? This nitrogen doesn't have just 3 bonds, it has 4 bonds. And if you actually wanted to write this out, you could write it out, you could show the structure. It would be CH3 hydrogen, hydrogen. It would look like that. Your 3 hydrogens, and then your CH3 is the 4th bond, or you could say one of the hydrogens is the 4th bond. And it has an overall positive charge. This is a shorthand for writing square brackets. If you don't really want to write out the entire square brackets, you could write it out like that as an abbreviated square bracket. Okay, how about this last example? Here's a molecule you've probably never seen before, but it doesn't make any difference. What's the conjugate acid of this molecule? We know this molecule is a base because it's basically a nitrogen, no pun intended. It's a weak base. It's an ammonia derivative. It doesn't matter what comes before the nitrogen. The point is the same. All nitrogens bonded to carbons, like ammonia derivatives are, behave exactly the same way. They use their lone pairs to grab onto hydrogens in solution. So the conjugate acid of this molecule will simply be the C5H11, nothing changes about that, NH2 plus 1 equals NH3, and then of course, because you're adding a positively charged proton to this neutral molecule, NH3 plus. And that's it. That's your conjugate. That's your conjugate acid of C5H11 NH2. It doesn't matter if you recognize the molecule or not. It makes absolutely, I could have put, it doesn't matter what comes before, I could have put XNH2. The point is that they all behave exactly the same way. The nitrogen goes out, grabs a hydrogen, and becomes XNH3 positive charge. You might ask, does it ever take on 2 protons? No, it can't. It cannot, because that would violate the octet rule, right? The maximum number of bonds that nitrogen can have is 4 bonds. So in both of these last 2 examples, the methylamine example and this example, the nitrogen already has 4 bonds. It had 3 bonds, and now it has 4 bonds with that with that proton added to it. So no, you can't take on more than 1. Here, let me just draw in case that's an issue. Okay, how about conjugate base examples? So how about hydrosulfuric acid, H2S? So we have hydrosulfuric acid. Let's say there's some sort of hydroxide ion. We'll use hydroxide ion as our stand-in, as our general stand-in for any base. Doesn't even matter, stand-in for any base at all. Just to represent bases, we'll say, okay, well, hydroxide ion is the base ion, right? So we'll use that. So what happens? Well, the hydroxide ion, being a base, will take one of the protons away from hydrosulfuric acid. So we start off with an acid, and then we end up with HS. So hydrosulfuric acid loses one of its hydrogens. How do I best represent this? I'm not really sure. -1. So we end up with HS. Of course, what's the charge now? Well, if we took a +1 charged hydrogen away from an otherwise neutral molecule, we end up with a negatively charged molecule, negatively charged ion, or negatively charged polyatomic ion. So we end up with hydrogen sulfide. This is the conjugate base of H2S. It derived from the H2S. So now we call it the conjugate base. What's the other side of this? The other side of this is H2O. hydrogen hydroxide, right? Which is water. Water, remember, water is the conjugate acid of hydroxide ion. Remember, these are all just relative terms. Water is not an acid all on its own, but in this context, water is the conjugate acid of hydroxide, which is a base. So we have the conjugate base of hydrosulfuric acid, which is hydrogen sulfide ion. It's the result of hydrosulfuric acid having lost one of its protons. Now, of course, you can go on, you can continue, and you can observe a second deprotonation. It would be very hard to strip away that last proton from sulfide ion, but you could do it. You could do it. And if you did, you would have sulfide ion as the ultimate conjugate base of hydrogen sulfide ion. So the very next thing would be HS minus. This is a very reversible process. It's a very weak acid. Of course, hydrosulfuric acid is a weak acid, by the way, as well. But you'd end up with hydrogen ion, of course. You'd lose your hydrogen ion, it would be detached, dissociated, and you'd end up with sulfide ion. The sulfide ion would be your conjugate base of the acid HS minus. Now, relative to its own conjugate base, hydrogen sulfide ion, or monohydrogen monosulfide ion, is an acid. So in this context, this would be the acid. In this context, it is the conjugate base. If somehow we could throw another hydrogen onto hydrosulfuric acid and make this H3S plus, that would become the acid, and hydrosulfuric acid, H2S, would become the conjugate base of that acid. But again, you define these things, you sort of get used to the way compounds act on a regular basis, not under extreme conditions. How about nitrous acid? Nitrous acid, HNO nitrous, remember? So that's nitrite with a T ion. So that's HNO2. So let's say we have nitrous acid. Again, when it loses a proton, and I'm not even going to specify a base or anything. I'm just going to say it loses a proton. It donates away one of its protons. So it has proton freely going somewhere. It doesn't really matter to us where it goes. That's not really the point of our discussion. And what's left? Well, what's left is the conjugate base, the nitrite ion. This is our conjugate base of nitrous acid. By the way, the stronger the acid, the weaker its conjugate base as a base. And the weaker the acid, the stronger its conjugate base. They're opposites. Let's see, so can I give you an example right now? I can actually. So nitrous acid is a weak acid. It's an acid, but it's a weak acid, right? That makes nitrite ion a relatively strong base, relatively strong base. It has a good tendency to pick up protons from solution. So nitrite ion can go around and it can actually grab protons from many other kinds of compounds, and possibly to a limited extent, even water. Now take the opposite. How about hydrochloric acid, one of the strongest acids? Hydrochloric acid's conjugate base is chloride ion. Strong acid, extremely weak base. How do we define a base? Remember, bases are proton takers or proton acceptors. So if I put chloride into almost any kind of solution, the odds of my getting this, the odds of chloride picking up a proton and forming HCl, negligible. Virtually no tendency at all. Chloride is an extremely weak base. It doesn't pick up protons. It does not accept protons. No protons accepted here. Cash only. So chloride plus hydrogen, not going to happen. And that makes some kind of intuitive sense, doesn't it? I mean, logically, doesn't that follow? If a strong acid, what defines a strong acid? Well, it's a compound that readily gives away its protons to anyone and everyone it wants to get rid of its protons. Well, if chloride was so easy and so eager to get rid of its proton, why would it reattach itself to a proton? It wouldn't. That makes chloride, the conjugate base of hydrochloric acid, an extremely weak base. Any conjugate base of a strong acid is going to be very weak as a base because that's how it ended up as a conjugate base in the first place. It let go of protons because it didn't want them. Weak acids, on the other hand, have a very limited capacity to lose their protons. They want to hang on to their protons. So because of that, that makes the conjugate base a relatively strong base because it really wants to take back that proton. That's why it was so reluctant to give it up in the first place. That's what made it a weak acid to begin with. That's what makes the conjugate base of that weak acid relatively strong. It wants its protons, whereas strong acids don't want their protons. Consequently, their conjugate bases also don't want their protons. So strong acids result in weak conjugate bases, and weak acids result in strong conjugate bases. And likewise for the reverse, for bases, strong bases give you weak conjugate acids and weak bases give you strong conjugate acids. Okay, hydrocyanic acid. How about hydrocyanic acid? So this, by the way, was just an example of a strong acid. So we already saw hydrochloric acid produces chloride ion as its conjugate base, and that turns out to be an extremely weak base. It has no tendency to pick up protons. That makes it, by definition, a terrible base. Chloride is an awful base because it doesn't want protons, and that's exactly what a base is supposed to do. It's supposed to pick up protons, but this one doesn't. Okay, hydrocyanic acid. Hydrocyanic acid is a weak acid again. So when it dissociates to a limited extent, and it produces what? It produces cyanide ion in solution, plus some free protons which go wherever the wind takes them, or wherever the solution winds take it. So cyanide ion, notice by the way, the conjugate bases are always negative. Going back, our conjugate acids are always positive. And that makes some kind of sense, right? Because what is the conjugate base? Well, it's what's left when you remove a positive one charged proton from a compound. Well, if you're removing one positive charge, you most likely end up with a negative charge because most molecules started out neutral. Likewise, why do we end up with positive charges for conjugate acids? Because the conjugate acid is what you get when you add a proton. When you add a positive one hydrogen ion to a neutral molecule, you end up with a positive charge. So most of the time you end up with positives and negatives for conjugate acids and conjugate bases respectively. So cyanide ion is the conjugate base of hydrocyanic acid, right? HCN acid. It's what's left after the hydrogen flies away. Here's one that's kind of unusual. And I actually put sodium amide, or sodium amide, or amide. I say amide. Sodium amide is a really super strong base. Amide, it's not the sodium that has any meaning at all. It's the amide ion, NH2 minus. That's nitrogen with two lone pairs. This is, well, I'll talk about it later, but right now, this is a super base, or very nearly so, a super base, the amide. It's called, by the way, the amide ion. Let me write this a little bit more neatly for you. The amide ion. And of course, this compound is just sodium amide. Amide is a polyatomic ion, just like any other polyatomic ion. But it has a unique characteristic that it's a very, very strong base. It's so strong that it will pull hydrogens off of compounds that we normally don't think of as acids. For example, this amide ion will actually reach over here and pull the hydrogen off of this alcohol, ethanol. Ethanol is not an acid. Don't let the structure fool you. This isn't a carbon, there's no double bond O here at all. This is not an acid, this is just an alcohol. Its reactivity is generally not that of an acid. It normally does not donate away any hydrogens from that oxygen. But this base is so strong that it will pull this off. So it'll take the CH3. So when we mix CH3, CH2, OH, and again, let me color code this. OH plus NH2, amide ion. The sodium is just a spectator ion, so we're not going to worry too much about the sodium. Who cares about the sodium, right? NH2. So what we're going to get is we're going to have the sodium come in and grab that hydrogen. So that what we get at the end of this is we get CH3, CH2 what? So if in this case, ethanol is our what? Is it an acid or a base? Well, I already said that the amide is a super base, meaning it's a base. Okay, so amide ion is our base. That must make, in this context, since this base is pulling a hydrogen, a proton off of ethanol, ethanol therefore must be our acid. Even though it's not technically an acid, remember, the only thing an acid has to do, or a compound has to do to behave like an acid and to fulfill the Bronsted-Lowry definition of acid, is donate away a proton. Well, it's donating a proton. Therefore, it is acting as an acid. So what would be the conjugate base? What's the formula for the conjugate base of ethanol? CH3, CH2OH. So the original molecule was CH3, CH2OH. Well, if it was an acid, and now we're looking at the acid minus one of its protons, what should we expect? Well, what we should expect is that we end up with CH3, CH2O with a -1 charge. This is called ethoxide. You don't have to memorize these names, by the way. This is not a, we've done all our nomenclature. We're not going to learn organic nomenclature. This is organic chemistry type nomenclature. You don't have to learn the name. I'm just for our purpose of discussion, I'm just telling you what these things are named, but you don't have to name. So this would be called the ethoxide ion. It now has become a negatively charged ion. Oxide, by the way, F means 2 carbons here, CH3, CH2. Oxide is this negatively charged oxygen now. This is the conjugate base of ethanol. Notice we have lost a hydrogen, and that's what is left. So even compounds that are not normally acids, even compounds that are not in the general scheme of things, acids can still act as acids. They can act as Bronsted-Lowry acids as long as they're willing to donate away their protons under the right conditions. What becomes of the amide ion, by the way? Well, the amide ion is no longer negatively charged, is it? We have NH2, and then we have what? Well, remember, the NH2 has gained a new hydrogen. So now it went from -1 plus 1, it is now neutral. This is now ammonia. So it turns out that ammonia, in this instance, is the conjugate acid of amide ion, NH2 minus. Or the other way you could see it is that amide ion is the conjugate base of ammonia. So it's all relative. And by the way, that's what I put over here. Here is exactly the reverse of what we were just looking at. So my example for you of a base acting as an acid is ammonia the base, ammonia, NH3, acting as an acid. So NH3 plus some sort of even strong base, and it would have to be pretty darn strong, by the way, because it's able to strip away a hydrogen away from something that's already a base. To take a hydrogen, a proton, away from a base that's already looking for more protons, not trying to give away its own protons, a base, another base that comes along that's even stronger can do so. Remember, these are all relative. It's like a pecking order. A stronger base will take protons away from a weaker base. A stronger acid will push protons onto weaker acids, if possible, if there's room for it. So we take some sort of super duper base, even stronger than ammonia. Well, actually, ammonia is not that strong. It's a weak base, but it has to be pretty strong in order to produce amide ions. So super base, we got a super strong base here. It removes one of the protons from ammonia so that we get the amide. And I have this written down anyway, but amide ion, or the sodium amide compound, and then we get some sort of conjugate acid of that base, which is H base with a positive charge. I should have probably indicated positive charge. Oh wait, no, I'm sorry. No, the base started off as neutral. Never mind. No, it should be neutral. What am I thinking? Yeah, the base itself, the ion without a negative charge, at a plus sodium is right over here. It's now joined with the amide ion that was formed as a result of this. It left the base that originally had the negative charge because it became neutral, and now it's with the amide ion, which lost its proton. So now it basically traded a proton for a sodium ion. This is kind of a double displacement reaction in a sense. So amide ion is the amide ion. So NH2 minus ion is the amide ion, another polyatomic ion, not very stable and very basic. The sodium ion is what's called a spectator. The sodium ion doesn't really do anything. It's only there for the purpose of keeping the charge balance in the solution. A solution can never have a net positive or net negative charge. All solutions, all mixtures must be neutral in charge, negative ions. Ultimately, all the sum total of all the ions in solution must sum to zero. Remember, you cannot have a negatively charged or positively charged solution. You'd be literally holding a beaker full of lightning. So if we go through and we label this, in this reaction, in this particular reaction, ammonia, which we normally refer to as a base, as a weak base, is instead going to be functioning as the acid in this particular reaction. Remember, it's always relative to what's going on around it. It's relative to the reaction. No compound is a base or an acid in an absolute sense. It's always about where it is, what other compounds are around it that can react with it, how it will react. Here, of course, it goes without saying that the base is our base, well, our sodium base is our base, okay. C is the spectator or counter ion. That's what sodium is functioning as. It doesn't really partake in the reaction itself. It simply gloms on to whatever the opposite charged ion gets produced. If the original base has a negative charge, it'll stick with the original base. If a new base is created with a negative charge, it'll go to that base. It goes wherever there's a negative charge. It's just there to neutralize charge overall in the solution. D is our conjugate base of ammonia. So D, conjugate base, specifically the conjugate base of NH3. Remember, whenever you say something is a conjugate base or conjugate acid, you have to refer to what it is the conjugate of. You have to spell out exactly what it is derived from that makes it a conjugate, and not in and of itself, in its own right, whatever you're saying it is. And then finally, you have H base, the entire compound, the H plus whatever, whatever B is, whatever the negative ion B is, whatever ion was strong enough to strip away a hydrogen from ammonia, that total compound is your base, and that is your conjugate acid. It now has an extra hydrogen that it can donate to some other compound. So this is the conjugate acid. And notice, by the way, this conjugate acid doesn't have a charge in this particular instance. So this is the conjugate acid of the sodium base compound. I didn't specify what the compound is. I couldn't think of something stronger than amide that was worth talking about. There are some things, but it's not really worth our discussion. It would just clutter up this scheme here. Okay. So now that we understand the concept of conjugate acids and conjugate bases, it's time for us to apply that concept to buffers. Buffers make heavy use of this conjugate acid, conjugate base concept, but only for weak acids or weak bases, one or the other. So a weak acid and its conjugate base, or a weak base plus its conjugate acid. These are what make a buffer. What is a buffer? A buffer is a solution that is designed to maintain a constant pH, or a constant concentration of hydrogen ions, or a constant POH, or a constant concentration of hydroxide ions. These are all saying the same thing. Remember, these four variables, or whatever you want to call these four parameters are all inextricably linked. If I change one of these things, if I reduce my amount of, for example, if I reduce my pH, I'm going to see my POH go up. I'm going to see my hydrogen ion concentration go up, and I'm going to see my hydroxide ion concentration go down. If I change any one of these parameters, all the parameters change. So when I say that a buffer is a solution designed to maintain a constant pH, it's designed to keep every single, by doing that, it keeps every single one of these constant. So it doesn't matter how I define it in terms of these. I could have easily said a buffer is a solution designed to maintain a constant hydroxide ion concentration. And it would be equally valid, because by doing that, it would also be keeping a constant pH and a constant POH and a constant everything. All of these parameters are constant. If one is constant, they're all constant. If one changes, they all change. So a buffer is just something to prevent change. The change and hydroxide ion. That's what a buffer is there for, to make sure nothing changes about those particular acid-base ions. So buffers are made from weak acids and their conjugate bases, or weak bases and their conjugate acids. And it has to be the related acid. It has to be the conjugate that is derived from that specific acid. You can't mix two different acids and bases together. You can't take a weak acid and then the conjugate base of some other acid. It won't work. Or it might not work right, or it might not work as expected. That's because all of this depends on equilibrium. And you're going to see a lot of these double arrows, these equilibrium arrows here. It depends on equilibrium. Remember, Le Chatelier's principle says that once a system is in equilibrium, anything you do to try and disturb that equilibrium will be counteracted by that equilibrium system. So this all depends on equilibrium, and the equilibrium comes from the presence of an acid and its conjugate base, or a base and its conjugate acid, weak acid, weak base. Remember, strong acids and strong bases don't have equilibrium. There is no reversibility for a strong acid or strong bases dissociation. They dissociate, and that's the end of the story. But with weak acids and weak bases, you actually have more complexity. You have a system, you can create a system that reacts to the environment. That's why living things universally use weak acids, actually mainly weak acids, although I suppose you could find a weak base somewhere in our system, in our bodies. So buffers work by having both an acid and a base in solution. However, it's not just any base. Remember, it is the conjugate base of that particular acid. They are related. The base and the acid are related through equilibrium. And equilibrium allows for a natural balance to be established and to be maintained. And remember, if you're maintaining, then that means you are keeping things constant, and that is the whole goal of a buffer. Our blood, for example, our blood pH is buffered at about 7.35 to about 7.4, a very narrow range, and that's entirely due to the carbonate, bicarbonate, and carbonic acid buffer system in our blood. So bicarbonate ion is the conjugate base of carbonic acid. Where does the carbonic acid come from? Well, blood is, like, by volume, I think it's mostly water, just like our bodies. So as you breathe in, or as your body generates carbon dioxide, or if you breathe in some carbon dioxide, or as your body generates carbon dioxide, that's probably the main source, your blood has carbon dioxide dissolved in it. Well, as the carbon dioxide in your blood combines with the water in your blood, you get carbonic acid. Remember, if you remember or watch the previous video, I talked about how carbon dioxide and water form the reverse reaction of the decomposition of carbonic acid. Carbon dioxide and water are a combination reaction that form carbonic acid, or hydrogen carbonate. But then that carbonic acid can also undergo a different reaction, not a reaction, but a dissociation of bicarbonate and hydrogen acting as an acid. So carbonic acid produces its own conjugate base, the bicarbonate ion. But this is a very weak acid. So because of that, you have an equilibrium established. There's a back and forth until you get a small percentage of bicarbonate ion, and most of it, so like 99%, remains carbonic acid dissolved in your blood or in the water, whatever system you're talking about. So there's reversibility here. If you try to make a buffer out of a strong acid like hydrochloric acid or nitric acid or sulfuric acid, it will not work. There's no reversibility. So taking nitric acid as an example, unlike these equilibrium arrows that are used here, for a strong acid or a strong base, I'm going to concentrate on acids only because acids are just I think they're a little bit easier to visualize because they're losing a proton. But everything I'm saying applies equally to bases. So imagine nitric acid loses its proton, so it donates away a proton. What's left? Nitrate. That's a one-way street. That's one direction. All 100% of your nitric acid gets dissociated. There's no more. The nitrate has absolutely zero tendency to reuptake hydrogen and reform nitric acid. So as soon as you put nitric acid in water, the nitric acid is gone. It's gone forever, and it's never coming back. So the only thing you have then is a cupful or a beaker full of nitrate ions and protons. That's it. Contrast that with a weak acid where you have, once you put carbonic acid into solution, what you have is you have three things in solution. You have a reservoir of protons in carbonic acid, you have bicarbonate ion, and you have protons. You have three different things in solution that can self-regulate, and that's the most important thing. The buffer works by being able to neutralize any added acid or added base to the solution above and beyond the natural equilibrium that gets established when you first put the buffer together, when you put the compounds together in the right proportion or the right concentrations. So the concentration of hydrogen ion and therefore hydroxide ion and everything else stays exactly the same. That's what you want. So let's take a look. I'm going to lay out the scenarios, then we're going to look at a visual representation of these exact same scenarios. I'm going to use acetic acid rather than carbonic acid only because acetic acid is monoprotic. I don't want any extra I don't want to, have this sort of mental overhead of wondering what happens to that second proton. But here I'll just take carbonic acid as an example. So we have carbonic acid partially dissociates into bicarbonate hydrogen. So take two scenarios. First scenario, if extra acid, i.e. hydrogen ions, are added to a buffering solution made of this, what happens? Well, you add extra protons. Extra protons increase the concentration of hydrogen ion. Okay, well, so far that lowers the pH. That makes it more acidic. So far, no advantage, right? Doesn't seem like there's an advantage. Increases the concentration of H+. Hey, wait a minute, we're supposed to keep the H+ concentration constant. What's going on? In the solution, causing the equilibrium. Aha, equilibrium is the key. It's the linchpin of this whole thing. An equilibrium, dynamic equilibrium. The whole phrase is dynamic equilibrium, but you can leave off dynamic. Dynamic equilibrium only exists with the reversibility of weak acids. The dynamic equilibrium that was previously established to become disrupted. What happens when you disrupt equilibrium? Nature fights back. According to Le Chatelier's principle, any disturbance in an equilibrium, once it's established, causes the reaction to try and counteract whatever disturbed the equilibrium. In other words, if I add too much hydrogen, what's going to happen? What's going to happen is too much hydrogen is going to flip this into reverse. Instead of being back and forth, there's going to be a net reaction in hyperdrive going toward the left, meaning the hydrogen, the extra hydrogen is going to combine with bicarbonate to reform H2CO3, complete molecule H2CO3. So the extra hydrogen ions are essentially mopped up. It's like somebody spilled acid, and now the bicarbonate is literally mopping up that extra acid and turning it into carbonic acid. By the way, this is literally true in lab. There's usually a container of sodium bicarbonate sitting around to mop up spilled acid. So this is actually kind of true to life, true to lab. Because there's bicarbonate, and because this, in this case, the conjugate base of carbonic acid, bicarbonate, actually has a somewhat strong tendency to reuptake hydrogens if conditions get to the point where there's too much hydrogen concentration around, you have this mopping up effect. Now imagine if this were a strong acid's conjugate base. What if this were chloride ion? Would chloride ion mop up? No way. No, chloride ion isn't going to grab any hydrogen ions and reform HCl. Absolutely not. That was a one-way ticket straight to ionization, straight to dissociationville. H plus Cl minus, 100%, straight arrow, left to right, never to return. Chloride doesn't do that. Chloride doesn't even like hydrogen ion very much. They were only together for a while just because they were in the gaseous state, and it seemed like the right thing to do at the time. So, but once chloride had its chance to get away from hydrogen ion, it did, and it's never been happier. So the excess hydrogen ions stick to the bicarbonate ion. This is because bicarbonate was happy with the concentration of hydrogen ions as they were. Once that concentration got too much, the hydrogen ions started crowding around the bicarbonate, and there was more of a chance for the bicarbonate to stick to the hydrogen ions floating in solution and forming neutral H2CO3. So in this way, the hydrogen ion concentration is maintained at the same level. You increase the hydrogen ion concentration, guess what? Bicarbonate makes sure that that concentration goes right back down again, and these get canceled out. So there's no change. Now, the natural question is this: well, what if I dump a whole bunch of proton in there? Buffers have their limits. They're not magic. If you dump like a gallon of strong acid into a beaker full of buffer, yeah, of course you're going to overwhelm the buffer. This is for small additions of acids and bases. Buffers are, like I said, buffers are not magic. They can't counteract anything you throw at them. It's within limits. Of course there are limits. If you have a 300 milliliter solution of buffer, no, you can't throw a liter of strong acid into that 300 milliliters and expect it to work. It won't work, it'll fail. But as long as you have just a reasonable amount of extra acid being generated or being added, the buffer can take care of that. Okay, that's scenario one. Scenario one is describing how a buffer can mop up excess acid. And we used hydrogen ion as the sort of stand-in for any old acid. Any acid will be represented by hydrogen ion. Now we're going to look at the scenario, what if more base, and we're going to represent base with the hydroxide ion because that's just the most obvious thing to represent a base with. What if you add more base, more hydroxide ion, in other words, to the buffer solution? How does the buffer solution take care of extra base? We can see that bicarbonate will mop up extra hydrogen ion. What's going to mop up the hydroxide ion? Well, I think it's pretty obvious, right? Well, yes and no. It's obvious, but not obvious. What ion do you see in this top equation up here? What ion do you see that will grab onto a hydroxide ion? What do you see that can make a compound out of hydroxide? While I'm erasing this, you think about it, or you can just pause the video. Well, what if I put hydroxide in there with this hydrogen ion? Doesn't that form water? Yeah, it does. It forms water. And as far as I know, water is neutral. So the hydrogen ion will neutralize the hydroxide ion. But wait, that's not a solution to our problem. That doesn't make things better. Because what does that mean? That means our hydrogen ion concentration as a result is going down. The hydrogen ion is being converted to water. Whoops, sorry about that. The hydrogen ion concentration is going down. The fact that it's neutralizing hydroxide has not helped at all. In fact, the hydroxide is having exactly the intended effect. It's destroying our proton concentration, our hydrogen ion concentration. So that's not it. That's not where the neutralization, that's not where the magic lies. Where does the magic lie? It's all about equilibrium. It's the equilibrium. That's the magic of buffers. That's the magic of weak acids and weak bases. Once this hydrogen ion concentration starts to drop, in a sense, the H2CO3 is going to sort of feel it. I'm speaking anthropomorphically, but H2CO3 and bicarbonate ion are going to feel the loss of hydrogen. And what's going to happen is the rightward reaction. Remember, in equilibrium, both directions of reaction are happening continuously. But without hydrogen there, you're lacking or you're reducing the amount of material to engage in the right to left reaction. As that slows down, you have a net relative increase in the left to right direction. So bicarbonate breaks down into, carbonic acid enhances or shifts to the right to produce more bicarbonate ion and to replenish the hydrogen ion concentration. So it shifts right. Equilibrium, we say that equilibrium shifts into hydrogen. It shifts rightward. Equilibrium shifts right to replenish the hydrogen ion because it senses the loss of that hydrogen by the fact that there's no feedback, there's no hydrogen ion, there's less hydrogen ion to combine with bicarbonate ion to keep the right to left momentum or the right to left process going. Remember, at equilibrium, both processes, the forward process and the reverse process, are always continuously going. But if you reduce hydrogen ion, the right to left, the reverse process slows down. The left to right process keeps going. So in essence, you're going to have a net increase in the rate of dissociation until the hydrogen ion concentration builds back up again. And then equilibrium gets restored with the same number, approximately the same number of hydrogens as before. So it's almost as if the equilibrium senses the decrease in hydrogen ion and then shifts into high gear toward the right-hand side, toward the forward process to replenish and regenerate the missing or the lost hydrogen ion. And the hydrogen ion, remember, was lost because hydroxide ion ate it all up, neutralized it, and turned it into water. The system doesn't care about water. It doesn't feel water. It just feels the loss of hydrogen ion. So in essence, another way to say this is that the carbonic acid is acting as a reservoir of protons. It's all it's all these hydrogen ions are dammed up, DAM, by the way. They're sitting behind a dam, and that dam is ready to release hydrogen ions only as the supply of hydrogen ions diminishes. Then this reservoir of H2CO3 releases hydrogen ions little by little to replenish the supply of hydrogen ions as needed. When the supply of hydrogen ions is no longer needed, the dam locks up and there's no more hydrogen ion released. It is this sort of sensitivity, this reactivity toward the environment. I don't mean chemical reactivity. I mean literally as if it's a living thing. These systems, these chemical reversible equilibrium chemical reactions act as if they are responding to what's going on around them. Like I said, it's no wonder that we living systems, all animals, creatures, cells, are mainly just a collection of a bunch of equilibrium reversible reactions. Because these kinds of reactions change with the environment. They are responsive to changes in the environment. Okay, let's visualize this. So I explained it in words, but let's actually take a look at what's going on here. And the next few slides are just going to be pictures like this. So buffer action illustrated. So the first example we'll look at is adding an acid, neutralizing added acid. So the hydrogen ion here, this hopefully you can see the difference in color here. This hydrogen ion here is burgundy. In fact, here, I'll even just draw a little sort of square around it just to indicate that this is a different hydrogen ion from the other hydrogen ions. The red hydrogen ions were the hydrogen ions that were already in solution as part of the equilibrium. That was these hydrogen ions right here. But the burgundy ones, the darker red ones, are the ones that are being added. We also have acetate in green, which I've abbreviated AC, acetate. These are green, these are the green boxes. Acetate ion. So we have red box, bright red for hydrogen ions that were generated as part of the equilibrium, part of the buffering system. And we have acetate ions in green boxes that were generated again as part of the buffering system. But then let's say, for example, and this is acetic acid. The AC minus here stands for acetate ion. I didn't want to keep drawing acetate ion, C2H3O2, so I just drew it as acetate, AC minus, I mean. Acetic acid is the whole thing. I'm going to designate that as HAC. That's HAC. Here, let me use some other color. How about bright blue, light blue? HAC. So we have HAC, that stands for acetic acid, our weak acid. Acetate, AC minus is our acetate ion, the conjugate base of our acid. And of course, hydrogen ion is our red. Now, the added acid is this dark red acid, the burgundy acid, the burgundy hydrogen ion. So let's say, for example, you set up this buffer solution and then you have, let's say your lab mate comes along, somebody in your lab comes along, they don't like you very much and they decide, you know what, I'm gonna mess with his project or her project. I'm gonna add a bunch of extra acid. I'm gonna add a bunch of extra acid and ruin their experiment. Jerk. Okay, anyways, this is fictional. There's nobody like that. I don't even have anyone in mind. Nobody ever did anything like that. So extra acid. So but you have thought ahead, knowing this person's ploys, you have thought ahead and you said, you know what, I'm going to buffer my solution. In addition to all the other things that are in my beaker, I'm also going to include an acetic acid-based buffer where I'm going to have hydrogen ions and acetate ions floating around in solution. And there's probably some spectator ion, maybe it's hydrogen ion and sodium acetate to add in those extra acetate ions just to make the buffer nice and robust. So he or she throws in some extra acid, which I'm going to represent by these H+ ions here. But what happens? Well, that extra acid, instead of reducing the pH, or in other words, increasing the H+ concentration, which is the same thing, by the way, reducing pH or raising hydrogen ion concentration. Instead of that happening, what happens? Well, we can kind of see what goes on here, can't we? These things don't happen. Why? Because every hydrogen ion that gets added is suddenly mopped up by an acetate ion. The acetate ions march forward like good little troops, and they attack the hydrogen ions and they form HAC. And remember, HAC itself, the complete molecule, has no effect on pH. So the extra added acid that would, or extra hydrogen ions that would have decreased pH or increased hydrogen ion concentration overall in the solution have been locked down. They've been neutralized by the conjugate base of acetic acid. The conjugate base is there to neutralize the added acid, conjugate base acetate ion. So you have a base in solution that is ready to react with added acid, but is not going to react with the acid that was part of the original solution. It's like the base can distinguish between an acid it's supposed to attack and an acid that it's not supposed to attack. It's like a very well-trained guard dog. It's guarding against extra acids. Neat, huh? So because of that, all of these hydrogen ions get locked down and get canceled out. You might say, well, what about the, so this builds up the hydrogen acetate or the acetic acid. The intact molecule concentration might go up slightly, but that's okay. There was plenty of it anyway. A little extra isn't going to hurt. Again, this is all within reason. If somebody dumps like a gallon of acid into your buffer, your little tiny thimble of buffer, yeah, of course it's not going to work. But this person's trying to be subtle, so they're not trying to overdo it. Okay, so that terrible plan did not work on their behalf because your buffer was able to handle the added acid by mopping it up with all these acetate ions. Notice you still have plenty of acetate ion, and of course you still have the hydrogen ions that are part of your normal buffer. Everything else remains intact. You lost a few acetate ions, but that's okay. That's not really going to affect you very much because there's so much acetic acid and so much acetate ion in solution. A negligible amount getting used up to counteract added acid isn't going to hurt. It's not going to change anything significantly. So that's an illustration of the neutralizing effect of the conjugate base of any extra added acid to a buffer. Okay, how about a buffer? How does a buffer neutralize added base? Well, we talked about this, but this is just sort of a picture of what goes on. Now let's say, okay, seeing that his plan or her plan was foiled, they come back, they say, okay, well, you're able to, this person doesn't know much about chemistry, I guess, for being in a research lab, or in some kind of a lab where they're working to destroy you. But anyway, let's say, okay, her dastardly plan did not work the first time. She says to herself, okay, well, the acid didn't work. I will instead put hydroxide ion. I will add extra base to ruin this person's project. So they throw in extra hydroxide ion. Well, again, we have an ion that is ready to go. The hydroxide ion, by the way, would have raised pH and would have lowered the hydrogen ion concentration. But again, neither one of those things ends up happening because instead, what happens? Well, the hydrogen ions that were already a part of the buffer system grab onto the hydroxide and convert it into plain old neutral water, which does not affect pH. Water, adding more water doesn't do anything. The extra hydroxide ion didn't get a chance to affect pH because it was converted into water, so it was canceled out. Hydrogen and hydroxide cancel out to water. Water, water, water everywhere, not a drop to drink. Water, and here, this one too, water. H2O. That's it, neutralized. Now, again, as I said before, wait a minute, but in the process of neutralizing the hydroxide, we are now down 1, 2, 3, we're now down 4 out of 8. 50% of our hydrogen has now disappeared. We only have 4 hydrogen ions left. That's where, oh, that's what I was missing. I needed to keep, that's where the hydrogen acetate or the acetic acid that is still floating around in solution comes into play. Unfortunately, I don't have a graphic to represent that, so I'm gonna have to draw that myself. So HAC is floating around in solution. So what will happen is the HAC, the acetic acid, is going to flip into high gear into the forward direction and is going to release more hydrogen into solution, thus replenishing and reestablishing the hydrogen ion concentration. So all those hydrogen ions that got neutralized by the hydroxide are going to be replaced by acetic acid, releasing more hydrogen ions, forming more carbon and more acetate ion, but also forming more hydrogen ion concentration. The additional acetate doesn't affect the pH. Remember, pH is only affected by hydroxide ion concentration and hydrogen ion concentration. So a change in acetic acid or acetate concentrations doesn't change anything. The point is that H plus is released by this proton reservoir of acetic acid. Acetic acid, our proton reservoir, releases hydrogen ion as needed, when needed, to replenish or to replace the lost hydrogen ion that went into canceling out that added hydroxide ion. So more H plus ions get generated by equilibrium. Both directions of the dissociation process are always in effect, but when one decreases, when one direction decreases, the other one keeps going and replenishes. So when needed, HA opens up the dam doors. The dam meaning the reservoir dam. So HA, acetic acid, this weak acid will open up the doors of the dam to release more of let flow more of the hydrogen ions. And when there's enough, it closes the doors and you don't have any excess hydrogen coming in. That's a metaphor, okay? Of course, it's only a metaphor. Obviously, unlike a real dam or reservoir, the flow is back and forth continually. It just happens to be at the same rate. Remember, equilibrium doesn't only go in one direction or no direction. It goes in both directions all the time, simultaneously, same rate at equilibrium. Okay. Now, what happens if we use a strong acid? Let's take, for example, hydrochloric acid. Hydrochloric acid, HCl. So we have our buffer here. Again, the red, the plain old red represents the hydrogen ions that were in there at the beginning, and the chlorides represent the chlorides there. Notice there is no HCl at all. No HCl present in solution at all. Unlike the HAC, the acetic acid, which is weak acid, there is no HCl present. No, I have it right here, no reservoir of hydrogen ions. Okay, well, let's see what happens. What if somebody, the same person, adds hydrogen ions to your HCl, your hydrogen chloride, or your hydrochloric acid solution? Well, those H ions, H plus ions, enter solution. Guess what happens? The chloride ion is not going to pick them up. Chloride couldn't care less about the hydrogen ions in its presence. There's going to be no bond formed between chloride and hydrogen ion. So those hydrogen ions simply exist there, and the hydrogen ion concentration increases, meaning the pH decreases. No buffering. Those numbers should be staying the same if this were buffered, but instead those extra hydrogen ions allow the pH to go down, meaning you get a more acidic solution, and the hydrogen ion molarity or concentration increases because you now have more hydrogen ions. So there's no buffering at all. So H plus, there's no defense against added acid. There's no defense against extra hydrogen ions, which represents any acid that you could add. Okay, what about hydroxide ion? I mean, surely that should help, right? I mean, we've got a bunch of hydrogen ions. Isn't that going to do something? No, because what happens? You put hydroxide ions in. Yeah, the hydrogen ions will bond to the hydroxide and make water, but that's not really helping things because now you have lost your hydrogen ions. So what happens? Your hydrogen ion concentration, okay, I can do better than that. Your hydrogen ion concentration has gone down. Your pH, therefore, has gone up. You don't want either one of those things to happen. If you want your solution to maintain a constant pH, you definitely don't want to raise your pH, and you definitely don't want to reduce your hydrogen ion concentration, which is the same thing. So because of that, yeah, it looks like hydrogen ion is doing something by neutralizing hydroxide, but at what cost? The cost of hydrogen ions. And that was the whole point, is not to lose any hydrogen ions. The point wasn't just to prevent hydroxide ions, although that would be bad too. It wasn't to prevent hydroxide ion concentration from increasing, but it was to prevent the loss of hydrogen ions. So in this respect, this solution of hydrochloric acid as a buffer is a total failure, because you're losing hydrogen ions in the process of neutralizing added base. In the process of neutralizing the added base, you are giving up your protons. So in essence, it's the same thing. You've lost hydrogen ions. And because of that, you've changed your pH, and that's exactly what a buffer is supposed to prevent. So a strong acid, and by the way, by extension, everything I said about weak acids and strong acids applies equally well to weak bases and strong bases. Weak bases can make great buffers with their conjugate acids, and strong bases would make terrible buffers for exactly the same reason you see here. There is simply nothing there to counteract the change in concentration of hydrogen or hydroxide ion, as the case may be. Okay, so picking compounds to make a buffer. So let's just do a little concept check here. Remember, the definition of a buffer is something that maintains a constant pH, and to make a buffer, you need a weak acid and its conjugate base, or you need a weak base and its conjugate acid. Oftentimes, though, remember, you can't simply grab a solution full of conjugate acid or conjugate base, because those are often ions. Conjugates, 99% of the time, conjugates are ions. You can't just grab a bucket or a bottle of ions, not just one charge, of single charge. There's no such thing as a chloride, well, let's not use chloride. There's no such thing as a fluoride ion solution, just fluorides. You can't find just fluorides. There must be a counter ion, or in other words, a spectator ion, something to neutralize the charge, not neutralize acid base, but neutralize charge. I can't just grab a bunch of F minuses floating around in water. There's no such thing. That would be lightning in a bottle. That would literally be negative ions blasting out of that thing, because they would be repelling each other. A buildup of negative charge never ends happily. A buildup of positive charge, likewise, never ends happily. So you need opposite. You can't even make such a thing anyway. You can't even make a solution that's made up of only negative ions or only positive ions. So I wouldn't want fluoride ions. I would look for sodium fluoride or ammonium fluoride or potassium fluoride, any kind of soluble ionic compound that contains my conjugate base or my conjugate acid, as the case may be. So let's take a look at these. So these are going to be combinations of acids or bases or just compounds, and we'll look at whether they can make a good buffer or not. Okay, so the first one, we have acetic acid and we have potassium acetate. Well, clearly this is a good buffer because we just used it as our example, right? We have acetic acid, that is a weak acid. What about potassium acetate? Don't let the potassium fool you. The potassium is our spectator or our counter ion. The potassium is just there to make sure that this is a neutral overall solution. What you should focus on instead is this negative ion attached to the potassium, is this the conjugate base of acetic acid? And indeed, it is the conjugate base of our weak acid. They should match, by the way. You shouldn't mix and match different acids and bases. You might have some success, but in general, try to avoid that because you don't really know where the equilibrium is going to lay or what the equilibrium is going to do if you mix two different acids and bases, conjugate acid and its base, or a conjugate or a weak base acid, Weak acid and its conjugate base, or the conjugate base of a different acid, or vice versa. So be careful about that. Just stick to related compounds and ions. How about the next one? We have potassium hydroxide and potassium chloride. Well, potassium hydroxide is a base. Okay, that's fine. But potassium hydroxide is a strong base. Automatically, that eliminates this. What about potassium chloride? Potassium chloride is if you were to see it as anything, it's really just the conjugate base of the strong acid. What's the strong acid? What does potassium chloride here represent? Well, remember, the potassium is just the counterion. What's the chloride conjugate base of? Hydrochloric acid, a strong acid. So this is a strong base and the conjugate base of a strong acid. This is completely meaningless. This doesn't do anything for us. And it's basically just a solution of ions. So we have, this is correct. This one is absolutely wrong. We can do nothing with this. It's totally worthless as a buffer. How about the next one? We have sodium bisulfate and sulfuric acid. Now, again, this is all about the context you're looking at. Sodium bisulfate on its own may function as a weak acid. Sure, that's a possibility, but what's with this sodium bisulfate? Do we see a conjugate base of this weak acid? No, we don't. This is a weak acid, and that's promising, but what's this? Well, this isn't a conjugate base of a weak acid. This is a strong acid. In fact, what we end up having is not a weak acid with its conjugate base, but what we instead have is a strong acid with its conjugate base, HSO4. And again, strong is completely useless for making a buffer. You don't accept anything strong to make a buffer, not as the major acid or base. Oh well, let's continue on then. So at least our first example was a good one though. How about this one? We have calcium fluoride and we have hydrofluoric acid. So hydrofluoric acid, let's focus in on the thing that's obviously an acid here. Hydrofluoric acid, what kind of acid is that? It's a weak acid, right? It's not on our list of strong acids. It's the only halogen that makes a weak acid. All the other halogens are strong acids. So this is a weak acid. Fluorine is the only halogen that makes a weak acid. Is this its conjugate base, calcium fluoride? Yeah. Why? Because calcium fluoride, assuming it can dissolve, will release a bunch of fluoride ions. Remember, the calcium is simply there to balance out charges. Just like sodium would be there to balance out the fluoride, calcium is there to balance out the charge of the negative on fluoride. The fact that there's calcium, a +2 instead of a +1, doesn't mean anything. It just means you can put in half as many calcium ions to get the same number of fluorides. So fluoride is the conjugate base of our weak acid. So we have a combination here. We have a solution made up of a weak acid and its conjugate base. So yeah, this is good. That would make a great buffer, assuming the ratios of the calcium fluoride concentration to the hydrofluoric acid concentration are decent. That's a topic for another time, meaning another chemistry class. You'll learn something in the future maybe called the Henderson-Hasselbalch equation, where you optimize a buffer for a certain pH range to buffer around a pH range. By the way, there's nothing at all that says a buffer has to maintain a pH of neutrality. You can buffer any pH you want. You can create a buffer to buffer around pH of 3 so that your solution always maintains a pH of 3, a very acidic pH. Or you can create a buffer that buffers around a pH of 9 or 10 or 11. You can buffer any pH value or range of values that you want. You just design the buffer in accordance to what you want. You can do that by tweaking the relative concentrations of the ionic compound that holds your conjugate and the ratio of that to your weak acid or your weak base. That ratio determines what the pH range you're going to buffer will equal. And you can move those around as you wish. Okay, let's go on to the next one. We have sodium nitrate. Okay, that's not looking good because nitrate is the conjugate base of a strong acid, and there's the strong acid. Strong acid, nitric acid, this is out. You can't make a conjugate out of something that's strong. It just doesn't work. This is out. Strong, as soon as you see a strong acid or a strong base, it's out. And this is the conjugate base of that strong acid. But just because you have an acid and a conjugate base in combination doesn't make a good buffer. It must be weak. Okay, finally we have ammonium hydroxide and nitrous acid. Well, ammonium hydroxide is a weak base. Ammonium hydroxide is a weak base. So that's looking good. However, nitrous acid is not a conjugate of anything. And if anything, it's just a weak acid that is totally unrelated to our ammonium ion, to our weak base. In fact, these two things are completely unrelated. This is just a weak acid in a weak base solution. At most, we can hope for some little bit of neutralization. We'll probably make some ammonium nitrite and some water, and that's it. It'll just be a minor reaction that won't really go all the way through, and that'll be the end of this. So this is not really anything. This is just a reaction waiting to happen. This is a neutralization. This is a neutralization reaction. When you put these two together, you're going to neutralize both. You're going to get ammonium nitrite in solution plus water. You'll get a reaction, but you're not going to get any kind of buffer solution. So that's out too. So the only two examples are the weak acid and its conjugate base and the weak, and again, a weak acid and its conjugate base. I just don't have that many examples of weak bases that can be used. We've concentrated far more, or the compounds we're far more familiar with in this class tend to be the weak acids rather than the kinds of weak bases. Those tend to veer off into organic chemicals, which we don't talk that much about in this class. This is just an explanation. This is the same thing we just talked about. I'm leaving this here in the PowerPoint for you to look over at your leisure without having to look at to watch the video. But do watch the video, obviously. Well, we're watching the video. At this point, you've watched the video. Let's see, that's it. That was everything I had to say about buffers. There's only one more video left, I think, at least for this topic, for acids and bases. I don't really plan on putting out anything else, but the next one we'll talk about titrations, which is mainly a lab experiment. Titrations having to do with neutralizing acids and bases and determining the concentration or the amount of moles in an unknown concentration of acid or base solution. So we'll take a look at that next time. So I hope all of this was informative and interesting. Please let me know how it's going. Let me know how you like these videos. If you saw anything, any kind of improvement or any errors or mistakes, let me know your thoughts. I hope you got something out of all this. I'll see you in the next video. Take care all.